Hi everyone, my name is Janelle Don A. Avila, and today I am going to discuss to you other construction surveys and construction surveys using total station instruments. So first, we have here the definition of construction survey according to Oxford Land Survey. A construction survey is a survey that presents locations and marks for construction activities. It is the process of executing evaluation and estimation prior to or during a construction activity. It is carried out to lay out engineering and construction works. Measurements are done for reference points, which determine the location of the planned structure improvements, vertical and horizontal positioning, dimensions, configuration, and to control the elevation of the new structures. The purpose of doing a construction survey is to maintain and establish the necessary vertical and horizontal control needed for a construction project. It includes taking measurements to ascertain quantities and then put these measurements in documentation to validate the final payments made to the contractor. And we have here some of the instruments used in construction service. We have here the tapes, clinometer, compass, magnetic locator, rods, reflectors and prisms, tripod, and theodolite. So first, we have other construction surveys. Other construction surveys include hydrographic surveying and underground surveying. So let us first discuss what is hydrographic surveying. The Constructor.org 2020 defined hydrographic surveying or bathymetric surveying as the survey of physical features that is present underwater. Hydrographic surveying is the science of measuring all factors beneath water that affect all the marine activities like dredging, marine constructions, offshore drilling, and others. This type of survey also take part in necessary data collection related to construction and the development of port facilities such as pier construction. So, hydrographic surveying is, as what it defines, is the surveying of what is beneath the underwater. For planning and constructing causeways, bridges, and offshore platforms, it is often necessary to conduct a hydrographic survey. These types of projects require special procedures to solve the problem of establishing horizontal positions and depths where it is impossible to hold a rod or a reflector. So, where can hydrographic surveying be applied to? Hydrographic surveying can be applied to dock engineering. That is where you can see the ports, the seaside, or the ships and boat docks. And hydrographic survey can also be used in irrigation. Irrigation is the process of applying controlled amounts of water to plants and at needed intervals. So, hydrographic surveying can also be used in land reclamation, where this land reclamation is the process of creating new lands from oceans, lakes, seas, riverbeds, and others. And another one is the water power or the hydropower. Water power or the hydropower is the power derived from the energy of falling or fast-running water. And this hydropower or water power is very useful. And one example of its usefulness is the hydroelectric power. Hydrographic surveying is also applied in flood control. So flood control is a method used to reduce or prevent the detrimental effects of flood waters. So like here in the Philippines, our country often experiences typhoons yearly. So we have to come up somehow with flood control plan to further reduce the damage that might be caused by a flood. So lastly, hydrographic surveying can also be used in sewage disposal or the disposal of the wastewater. So sewage disposal is the process of removing or destroying or converting the harmful substances that are found in the sewage, and it is by means of ammonification, nitrification, or even bacterial action. But I won't further discuss this because another group has the wastewater treatment, as I have recalled. So they're going to discuss what this is all about. So moving on, we have here the uses of hydrographic surveying. So hydrographic surveying can be used to determine the depth of bed and shorelines. This is necessary because when you are to construct a bridge or perhaps a infrastructure in the bodies of water, you have to know the depth of the water to identify the materials to be used in constructing the said infrastructure and to test whether this area is safe for constructing the structure. So hydrographic surveying can also be used in locating sewer fall by measuring direct currents and the mean sea level. So hydrographic surveying can also be used in identifying the irregularities of the underwater bed. So it is important to know the irregularities of the underwater bed because in constructing, the engineers shall know what irregularity is beneath underwater. The land found underwater may be sloped or may be crooked or it may be has a hole, so they need to know that to identify whether it is safe to build something in that area. So hydrographic surveying can also be used in measuring the tides and the river and stream discharge. And this survey also is useful in planning massive structures like dams, rivers, bridge, docks, harbors, seaports, and many other structures relating to the bodies of water. And lastly, hydrographic surveying can be useful in preparing a navigation chart. This nautical chart is a graphic representation of sea area and adjacent coastal regions. Depending on the scale of the chart, it may show depths of water, heights of land, and other features. Now let us proceed to the underground surveying. The Constructor.org defined underground surveying as survey operations performed beneath the surface of the earth in connection with tunneling, exploration, and construction in subterranean passageways. And this underground surveying is very different from the normal surveying that is done on the surface. And here are the reasons why the underground surveying is different from the surface surveying. First, in doing the underground surveying, you need to have artificial lighting in order to see the equipments beneath the ground because in underground, we have poor lighting. Second, the working space in doing underground surveying is very cramped or very narrow. So third, instrument stations and benchmarks for leveling must be often set into the roof of a passageway to minimize disturbance from the operations being carried on in the workings. So since the passageway to the underground is very narrow, some instruments must be placed in working underground. Fourth, instrument stations are set with some difficulty since plugs must be driven into drill holes in rocks. And lastly, underground workings are wet with considerable water dripping from the roofs of passageways and running along the floors. So since underground surveying is done beneath the earth's surface, it's expected for the workplace to be wet. So the major application of this underground surveying is the construction of tunnels and other underground utilities. The tunnel is constructed when open excavation becomes uneconomical, usually when it is more than 20 meters. It reduces the grade, shortens the distance between given points separated by a dividing mountain or a ridge. Underground surveying meets the demand of modern rapid transit in the city. We can also have exact alignment, proper gradient, and establishment of permanent station, marking the proposed route. So, why is tunnel very important? Tunnels are very important because these tunnels are used for transportation. They could be used for carrying freight, passengers, water, sewage, and etc. Tunnels are more economical because tunnels avoid disturbing or disrupting with surface life and traffic during construction. So that is all for the underground surveys. And now let us move on to the construction surveys using total station instruments. First, we need to define what is a total station. So according to civilsimplify.com, a total station is an electronic or optical instrument that is used in modern surveying and building construction that uses electronic transit theodolite in conjunction with electronic distance meter or EDM. This total station is also integrated by a microprocessor, electronic data collector, and a storage system. The total station is used to measure sloping distance of object to the instrument and horizontal and vertical angles. The microprocessor unit enables for computation of data collected to further calculate the horizontal distance, coordinates of a point, and reduced level of a point. Data collected from total station can be downloaded into computers or laptops for further processing of information. So before we are going to use a total station instrument, it is necessary to orient the instrument. Depending on the type of project, horizontal or both horizontal and vertical orientation may be needed. For example, if just the lot corners of a subdivision are being staked, then only horizontal orientation is needed. We have three commonly used methods in the horizontal orientation. We have the number 1, azimuth, number 2, coordinates, and number 3, resection. Azimuth and the coordinates apply where an existing point is occupied, while the resection is used when the instrument is set up at a non-control point. In azimuth orientation, the coordinates of the occupied control station and the non-azimuth to a backside station are entered into the instrument. If the occupied station's coordinates have been downloaded to the instrument prior to going into the field, it is only necessary to input its point number. The backside station is then sighted, and when completed, the azimuth of the line is transferred to the total station by a keyboard stroke, whereupon it appears in the display. Second, the coordinate method of orientation uses the same approach, except that the coordinates are both occupied and the backside station are entered. This data could have been downloaded previously, so that it would be only necessary to key in the numbers identifying the two stations. The instrument computes the backside line's azimuth from the coordinates, displays it, and prompts the operator to sight the backside station. Upon the completion of the backside, the azimuth is transferred to the instrument with a keystroke, and it appears on the display. In the resection procedure, a station whose position is unknown is occupied in the instrument's position determined by sighting 2 or more control stations. This is very convenient on projects where a certain high point of elevation in an open area gives good visibility to all points to be staked. As noted, 2 or more control points must be sighted. Observations of angles and distances are made to the control stations. The microprocessor then computes the instrument's position by certain methods. The conditions of the projects will normally dictate what orientation to use. Regardless of the procedure selected, after orientation is complete, a check should be made by sighting another control point and comparing the observed azimuth and distance against their known values. If there is a discrepancy, the orientation procedures should be repeated. It is also a good idea to check orientation at regular intervals after stakeout has commenced, especially if it is a large project. In fact, if possible, a reflector should be left on a control point just for that purpose. Now we will go to the vertical orientation of a total station. So vertical orientation of a total station can be achieved using one of two procedures. The simplest case, of course, if the elevation of the occupied station is known, and then it is only necessary to carefully measure and add the HI or the height of instrument to the elevation of the point. If the occupied station's elevation is unknown, then another station of known elevation must be sighted. We have here an illustration where the instrument is located at station A of unknown elevation and station B whose elevation is known and sighted. From slope, distance S, and zenith angle Z, the instrument computes V. Then, the HI or the height of instrument above the point is equal to elevation B plus the HR minus V, where HR is the reflector height above the station B. As with horizontal orientation, it is a good practice to check the instrument's vertical orientation by sighting a second vertical control point. Once orientation is completed, project stakeout can begin. In general, staking is either a two-dimensional or a three-dimensional problem. We have here under the two-dimensional, which are staking lots of a subdivision and layout of horizontal construction. And under the three-dimensional, we have slope taking, blue top setting, pipeline layout, and butterboard. For two-dimensional stakeout, after the file of coordinates for all control stations and points to be staked is downloaded and the instrument is oriented horizontally, the identifying number of a point to be staked is entered into the instrument through the keyboard. The microprocessor immediately calculates the horizontal distance and azimuth required to stake the point. With total station having robotic capabilities, the instrument will swing in direction to the proper azimuth without any further operation intervention. With a high order of accuracy using total station instruments, stakes quite distant from the instruments can be laid out, and thus many points set from a single setup. In fact, an entire project can be staked from one location. This is made possible in many cases because of the flexibility that resection orientation provides in instrument placement. So that encompasses what I need to discuss to all of you regarding the other construction surveys and the construction surveys using total station instruments. I hope you have learned something in this video, and